In the previous session, we started with the boundary conditions being applied to the rectangular waveguide and the wave uh, propagation along the z-axis such a way that Ez equal to 0. That's a transverse electric wave. Okay. We applied the boundary conditions, what we see here, right? Four various boundary conditions have been applied, and we obtained the equation of Hz represented by equation number 9 over here, right? So that takes care of a constant and the time as well as the z-axis, right, into the variation, right? We consider that. Then we also have identified what will be the various field components other than z-axis. So Ex, Ey, Hx and Hy represented by the respective equations, right? Then we identified what are the modes that are present, right, in this TE wave, right? So we understood that TE00 is the one which does not exist. Other than that, all other fields, since at least two of the fields do exist in other cases, we have the T01, T10, T11, etc. existing in the rectangular waveguide, right? And under the transverse electric mode of operation or mode of wave propagation. All right, now we'll discuss about what is called as the dominant. Right, now if you want to define the dominant mode, it is that mode for which the cutoff wavelength, right, has the maximum value, right? So this is that particular mode, that mode of wave propagation for which the cutoff wavelength, the cutoff wavelength is maximum. Okay, whichever mode shows that, we'll try to call that as a dominant mode. All right, now let us try to substitute the equation. Okay, we know the equation for lambda c for given values of m comma n, right? If you remember, we already have used this particular equation, right? Once when we discussed about the Tm transverse magnetic wave. All right, so I am going to use the same equation. Just see whether you can recall, right? 2ab divided by a root of, this is m square b square plus n square a square, right? This is the cutoff. So let us try to substitute and get the values of various cutoff frequencies of various modes possible, right? So first I want you to calculate TE01 mode, in the sense m is equal to 0. So I'm going to call that as lambda cutoff for 01. Right, so you see m is equal to 0, so m part will not come into picture, right? Only the n part is equal, n is equal to 1, m equal to 0. So I have to write this is 2ab divided by under root, this is a square, n is 1, so a square, so a will be cancelling out, correct? A cancels from the numerator and the denominator, so I'm left out with b, 2b. Okay, so I can write the answer 2b. That is for TE01. Is it okay? Next, let me move to the TE10 mode. TE10 mode, I'm going to call that as lambda c of 10. So that is lambda c of 10. So in this case, you can see that the numerator is still same, 2ab divided by, this is under root b square, isn't it? So b cancels, I'm left with a, so that is 2a. That is the answer. Are you okay? Now let's go for the other one, that is TE11. This mode also exists, correct? So I can call that as what shall we write? This is lambda c of, right, lambda c of 11 all the terms will exist, right? So 2ab divided by m is 1, so I'm going to have b square plus a square, or a square plus b square. Okay, now I have a question, right? Out of these three, which is maximum? Which is going to generate the lambda maximum, right? Just to recall that, what are the dimensions? Okay, what are the dimensions of our waveguide, right? The waveguide is somewhat like this. Okay, so it's placed in this way, right? I slightly move to right so that I can see this, right? So this is how the waveguide is present. So if this is 0, this is A and this is B. So A is the larger dimension compared to B. So just remember this one point when you try to answer my question. Okay, so my question is that out of the three terms which you see here, right? Lambda C01, lambda C10, lambda C11. So I have a question that you need to find out which is the bigger one out of these three lambda cutoff values, which is the one that has the larger value. Out of the three lambda values, that is lambda C01, lambda C10, lambda C11, which value will be the highest one? Which is the largest lambda, largest cutoff wavelength? Lambda C11. Okay, so in that case, you see the denominator, right? In all the three cases, you see numerator is same, 2ab, 2ab, 2ab. Okay, so in order to make a specific term to reach its maximum value, denominator should be minimum. So out of the three denominator, which is minimum, you need to find out. A square plus b square is larger compared to a square or b square, isn't it? So third one is not the answer. It's okay. So you see, if I say that I have a number 3 and number 4, right? I am comparing this 3, 4 and another number which is 3. So maybe it is 3 square plus 4 square, and my next number is 3 square plus 4 square. Which number is smallest here? Even if you take the square root, it still remains same. The same property will be maintained by them. So it doesn't matter whether you have a square root. Okay. Yes. Yeah. So think in that way and try to answer. No, I already know the answer. Which one is bigger, A or B bigger? I already know. You just look at this diagram. Which is bigger? A is bigger, right? So B is smaller. So what is your answer now? Which is the, oh, right? Lambda C10, right? That's correct. So I have to have this is as the largest value. Okay. So I will just write one point here. This justifies everything. So since in the rectangular waveguide, always A is bigger than B, right? That is our convention. A is a larger dimension than B, right? This means lambda C10 is the largest wavelength, isn't it? Wavelength. So that means the TE10 is the dominant mode. That is a dominant mode, right? How to find out the maybe normally people ask just a 1 mark question or something like that on this topic, direct questions, so which is the dominant mode. But if they ask you to derive also, you can do that, because we know the equations and we know the conditions to be applied, so that we can declare which is the uh, dominant mode. Okay, that's one thing. Other than this, we need other equations to solve some of the problems. Okay, so I'll write the equations required, right? So that we can apply those equations and we can solve the problems, right? So the other equations that we use whenever we try to solve some problems are like this. One is beta, right? So that is general equation. Most common equation is 2 pi divided by lambda g, right? But I can also use another equation, that is omega square into mu into epsilon minus the omega c square cut off, okay, omega c square into mu into epsilon. So mu epsilon I can take it out also, but anyway, ultimately we can do this, right? So root of omega epsilon times root of omega square minus omega c square is the equation. Okay, one more is the Vp, the phase velocity, right? Just recall this equation. This equation will remain same when compared to the TM mode, right? Transverse magnetic waves also will follow the same properties, right? Compared to the transverse electric wave when they are propagating inside the rectangular waveguide. Okay, so this is true only for the rectangular waveguide, but anyway, so we know that this equation holds good. So that is 1 minus the lambda divided by the cutoff lambda c, the whole square. Is it okay? That is Vp. If you want to go for a Vg, the group velocity is, it can be calculated in this way. So I'll write c times, c is the velocity of light in free space, this times 1 minus lambda divided by lambda c the whole square, right? You see that the root term comes to the numerator. That's all. That's the difference. And also I can try to write an equation for lambda g if required. That is in terms of, this is the guided wavelength, right? Do you remember the term guided wavelength? Yes, it's that. So this is lambda divided by under root 1 minus the lambda divided by lambda c the whole square. Okay, right. So same four equation we already have come across. So I'll directly write their values for the TM waves, sorry, TE waves, and we can use it if required in the problems. Okay, beta, Vp, Vg, and lambda g. All right. So let's move to the next concept. That is, it's an important concept, and it is called as the wave impedance. Okay, so this is wave impedance. Now, actually, this concept, the initial part of the concept we already have studied in the electromagnetic waves or maybe in the field theory, right? So I'll directly borrow the definition of whatever we used over there. Okay, so wave impedance is a ratio. Okay, it's a ratio of the electric field to the magnetic field, right? This is a very fundamental definition, right? Whatever we applied in electromagnetic waves, maybe in some other subject, is like that. It simply says that it's a ratio of electric field to a magnetic field of a wave. But now we are not going to use that rough definition. We are going to be an accurate definition here. Okay, the accurate definition for the wave impedance is like this. Okay, before that, let me write the notation. This is ZZ. Okay, Z for impedance. Again, Z for most of the time it is used as a directional form. Okay, wave when propagates in the Z direction, what is the impedance? Okay, right. So that's what is the notation stands for. But anyway, let me try to write the definition. So the wave impedance, is, it is defined as, it's still the ratio of, now you see, I'll write the field strength, that is the is of, okay, the strength of the strength of electric field in a transverse direction in a transverse direction the to the strength of the magnetic field along another transverse direction. So for example, let's see the meaning of the transverse. Okay, so transverse means I know that the TEM means no electric and magnetic component along the direction of wave propagation, correct? Okay, but I'll use a coordinate system diagram here to understand what exactly we mean by electric field in one direction and magnetic field in the other direction. That's what we can see here, right? So the definition says I'm talking about the electric and magnetic fields of that type, correct? Okay, now, so this is what I mean. Now let me mark the directions. Okay, let me say that I have the electric field along this direction. So Ex is this way. So I will be having I should have at least one component Hy so that you have the wave propagating in the Z direction. Okay, right? So that's one of the definition. If at all you want the wave to be propagating in the opposite direction, right, then I should have E here. This is Ey, but it is negative because it is going downwards. Okay, so anyway, I don't want to put a sign here. Let's define that properly when we use it in the equation. So I don't want to write plus and minus here, that there may be a confusion at a later stage. Okay, right. And the field along this axis, it should be say Hx, right? At least two of the components should exist so that the wave propagates in the Z direction. So that's the whole idea. All right, the concept is simply that. Okay, all right, now let's try to define according to the definition we have given. Let us try to define the ZZ. Okay, so therefore the ZZ wave impedance ZZ is equal to either you use Ex divided by Hy, or you can use minus of Ey divided by the Hx. Right, so these are the definition. Also we can apply, there is another form in which we can calculate the ZZ, that is equal to take a root and add them. So that is Ex square plus Ey square divided by under root Hx square. All right, so this is Hx square plus Hy square. Are you okay with that? Fine. So this is the most general format. I'm going to call this as equation number 1. But now we will look at the wave impedance, maybe specific to a given type of wave. For example, transverse magnetic wave. For TM wave, right? Anyway, I'll start with the same definition I just have given. ZZ is equal to, what is that? ZZ is equal to, I'm going to call this is the Z of the TM wave. All right, doesn't matter, it's the same notation, right? Z of a wave, I have to use either this Ex by Hy. Okay, so I'll use the first definition we have used, that is Ex divided by Hy. right? So just to recall, we have the equations present for each of the field component, correct? Ex has an equation, Hy has another. So let's try to substitute and then get a value. Okay, so this is minus gamma divided by h square, partial derivative dou Ez divided by dou x. Subtract from this j omega times the mu. So I think I have a minus j omega mu divided by h square, and we have partial derivative dou hz divided by dou y. This is the numerator part. Let me substitute the required denominator as well. Okay, this is dou y. Okay, then I divide this by. Now this is once again minus gamma divided by h square dou hz by dou y, dou hz divided by dou y, again minus j omega epsilon by h square dou ez dou x. Okay, so we have this. Now as a TM wave, right, what is the condition you substitute? So TM wave means I have to substitute the hz should be 0. There is no magnetic field. Okay, and also I will make an assumption here and assume that the gamma can be simply replaced as j beta. It's a lossless case. Okay, alpha is not, there is no alpha, simply you write j beta. Okay, so fine. Assuming that, in the sense, if air is a medium, it's lossless. If you have some medium present in over there, it becomes loss. All right. Okay, so therefore the ZTM becomes equal to the first part will exist over there, so that is minus gamma divided by h square dou Ez divided by dou x whole divided by, this is minus j omega epsilon divided by h square into, this is dou Ez by dou x. All right, so I think the dou Ez will get cancelled in the numerator as well as the denominator. Okay, so dou Ez by x, this will cancel. I can see that minus cancels with this minus. Okay, also I can see that the h square getting cancelled, right? Perfect. So that means you can see that I have the gamma over j omega epsilon, isn't it? But I just made an assumption that gamma is equal to j beta divided by, so I can substitute now. So therefore this is j times beta divided by j omega epsilon, right? So that is equal to beta divided by omega times epsilon, isn't it? Okay, now I just have written one equation for beta in the previous set where we wrote some of the equations, right? Let me quickly show you that. So various equations, you can see that beta has an equation in terms of, one is that, and I'll use the second one, root of omega square minus, right? Let me substitute that part over here for beta. So that is now, so this becomes equal to under root omega square mu into epsilon minus omega c square mu times epsilon whole divided by omega epsilon, isn't it? Correct. So let me take out the mu into epsilon out, root of mu into epsilon into root of omega square minus omega c square divided by omega epsilon. So this in with this case, so we can see that this divided by, I'm trying to write a root, it's not root, so in the denominator I don't have a root, right? Simply omega epsilon, correct? So the numerator cancels and I'm going to get a root in the denominator, right? So what is 1 by root omega epsilon, if you remember? Omega Oh, okay, okay. I cannot cancel, right? Sorry, I made a mistake. Big mistake. Omega cannot be cancelled, right? Epsilon can be cancelled, but I cannot cancel the omega, isn't it? I made a mistake. Sorry, I'll correct. So right now I have omega into epsilon, out of which I'm able to cancel. I'll correct. I think this I cannot cut, right? As a whole, I cannot cut. I'll split and write. So I will write this is root of mu into root of epsilon. I'll write, out of which root epsilon cancels with a root here. So this, whatever term you have in the denominator, you get a root for. Okay, root of epsilon. I hope this is fine, right? I get a root of epsilon in the denominator. Numerator root cancels. So now I can try to write this as follows. So this is equal to under root. Mu has a root in the numerator, epsilon has a root in the denominator. Then rest of the terms I can write as it is. So I'll take the omega inside. What happens when omega goes inside? Omega square minus omega c square by omega square. Correct? Omega when goes inside the square root, it becomes a square. So this is root of mu by epsilon times root of omega it will cancel 1 minus omega c by omega the whole square. Correct? Are you okay with that? That means what is omega? Omega is 2 pi f c. Correct? So I'll further simplify. This is mu by epsilon times root of 1 minus 2 pi f c by 2 pi f whole square. 2 pi cancels. So because of which I'm going to get my equation. Either this is the equation if you have omega readily available with you. Otherwise, so this is ZTM. So otherwise, the option is you can write mu by epsilon under root. This is into square root of 1 minus fc by f whole square. Okay, that's one term. Otherwise, we can actually further simplify c by f. So you can actually multiply and divide by c to the term, and we can actually simplify. This is the second equation for ZTM. I'll write a third equation as well. This you can get if you want to modify, then you can modify and you can get this. Otherwise, I can try to write it in this way. So this is root of mu by epsilon. What if I want to write in terms of lambda? Okay, so that is 1 minus, this is lambda by lambda c the whole square, right? Either use the first equation for Tm, second one, or this third one, right? Any equation you can use and you can calculate the ZTM. Okay, now we try to bring a new concept before we go ahead. This is called as an intrinsic impedance. All right, so let's try to write what is called as intrinsic impedance, right? That is the okay, let me try to define that first. Anyway, I'm not going to write a definition here. Let's just define. Okay, the intrinsic impedance of it's with respect to air we are talking about. Okay, whenever an electromagnetic wave passes through air, air offers some kind of resistance to the propagation of the wave. How much resistance it offers, it is called as a intrinsic impedance of air. Okay, similarly, when that particular wave enters into a medium will offer a different resistance. Okay, it is called as intrinsic resistance of that medium. Okay, right. So let's try to define the intrinsic impedance. Intrinsic impedance. So let's try to define this now. The intrinsic impedance is the impedance offered by any medium to the electromagnetic wave, electromagnetic wave propagating through that particular medium. Okay, so that medium, it is right, denoted right. So let's first calculate for air. I know that this is defined as eta, intrinsic impedance, which is simply the root of mu naught by epsilon. Okay, mu naught has a value 4 pi into 10 to the minus 7 divided by the epsilon value is, what is the epsilon naught value? Okay, so there is one value 1 by 36 pi into 10 to the minus 9 under root. Okay, this is one of the value of the epsilon. Otherwise, we can even, if possible, we can even remember the, I think 1.6 into 10 to the minus 9, right? No, that's not. I think epsilon naught is 8.854 into 10 to the minus 12, right? Yeah. You can use that. Anything you use, please calculate this value and get me the answer. So when we simplify this, we get an answer approximately 377 ohms. So it's actually, we can understand that this is a resistance value, right? As per the definition, this is the resistance offered by air whenever any electromagnetic wave propagates through that, like light. Okay, whenever light propagates through the air, it feels that there is a resistance of 377 ohm to that. Okay, so that's what is the meaning. So if you want for any other medium, right, I have to use this. So for others, right, the fe this sorry, the intrinsic impedance is nothing but, right, correct, I'll write this as eta naught. Okay, so that is the eta naught, that is 377 into root of mu r divided by epsilon r. Or you can directly write 377 times root of the mu r of that media divided by epsilon r of that media. That's all. Okay, right, now I can update my above equations. Previously we written equations of ZTM, therefore ZTM can be written like, I'll write only one of them, that is directly you can write 377, or in general it is this eta value, right? So that is equal to eta times square root of 1 minus the lambda by lambda c whole square, right? Other equations also you can use, but the eta will remain there as it is. Okay, right, let's move ahead. Now we need to calculate the z value for the transverse electric. Okay, so that is for TE waves, what happens to the zz, right? I'll directly define, I'll use the equation. So zz is equal to, I'm going to call this as ZTE, all right, that is equal to Ex divided by Hy corresponding to the TE wave. So let's write the equations of TE waves components, all right. So this is minus of gamma divided by H square dou Ez divided by dou X minus j omega times mu minus, I can write the j omega times mu divided by h square into dou hz divided by dou y, That's the numerator term. Denominator will be minus gamma by h square. This is dou hz by dou y minus j omega times epsilon divided by h square. It is dou ez, I think dou ez by dou x. Okay, so dou ez by dou x, right? So that's divided by. Okay, so what is for a TE wave? Let's make an updation, right? That is Ez transverse electric, right? So Ez equal to 0. And we'll also make an assumption of the lossless case where gamma can be replaced by J beta. Okay, so we'll substitute this gamma equal to J beta in our equation that is above, right? So that implies the Z of the transverse electric wave should be equal to, so wherever I don't have a Hz, right, those terms will be cancelled. The first and the second term, first term in the numerator, second term in the denominator will get cancelled. Okay, so because of which I can write minus j omega times mu divided by h square into, you see, this is dou hz by dou y whole divided by minus of gamma divided by h square. This is dou hz by dou y. So dou hz by dou y will be cancelled in both numerator and the denominator. Okay, then I can also cancel the h square term. Okay, so we can cancel the h square here, h square there, and also the negative terms will be cancelled. So after that, I am left with the j omega times mu divided by gamma. Correct? So what can I substitute for? Okay, I can substitute for denominator as discussed. Put the denominator value, that is wherever I see a gamma, I'll put this. So j omega mu divided by, this is j beta. So j cancels. Simply we can write omega mu divided by beta, isn't it? Okay, now how do we simplify? Like, can we substitute the beta in the same fashion we did earlier? I think yes. Okay, so this I'm going to write as follows. So this is equal to, keep the omega mu as it is in the numerator. Okay, so that is omega mu divided by, substitute for beta, I'll take a root of omega into epsilon outside. Then I'll write the remaining terms as omega square minus omega c square. Okay, one step I skipped here. And right, I think I made a mistake here as well. Right, so it's not omega epsilon, it is mu into epsilon. Denominator term is, okay, so let me update that. So this is mu into epsilon. Right, so this root mu cancels with the numerator getting a mu over there. So I can write now this is equal to, once again, root of mu by epsilon times, I'll write 1 divided by, I'll take the omega to the omega inside this, right? So that is omega square minus omega c square divided by omega square, right? What is root of mu by epsilon? That is the eta, right? The intrinsic impedance, that is eta divided by equation, that is 1 minus omega, can I write omega c by omega? Yes. Okay, so this is 1 minus omega c by omega the whole square. This is ZTE. I will update this. This is also equal to, you try to write in terms of the frequency, eta divided by 1 minus fc by f, its square under square root. Okay, or just now we have seen that how do we convert, right? So how to convert this equation into the lambda terms, how to write it in the form of lambda, we know that, right? So let us try to substitute that here. when we try to write the same equation in terms of lambda, fc gives you a lambda c, f gives you a lambda, but their positions get interchanged. That's all. Okay, denominator goes into the numerator and the numerator becomes to the denominator. So that's the term we need to consider. Okay, so this is equal to, therefore, this is equal to eta divided by 1 minus, this is lambda by lambda c whole square under the square root. Okay, these are the three equations corresponding to the Z or the ZT transverse electric mode of wave propagation with the value of the wave impedance. Okay, but remember one point, I think we have discussed this in the electric field, or as I remember it, we have discussed this in the electromagnetic waves, right? So there is a concept, because every the electromagnetic wave we studied in that chapter will be only TEM. So this is going to be TEM mode. Okay, we never studied TE, we never studied TM or any other hybrid modes, right? We assume that everything is a TEM. So ZTEM will not be changing. ZTEM will be the eta value of the medium itself. Okay, for transverse electromagnetic wave, the amount of impedance is intrinsic impedance itself. Okay, it will not change. But for ZTE and ZTM, the intrinsic impedance will change to get a wave impedance. Are you okay? Okay, now fine. I think we have covered the all the equations related to the Z values. Okay, the wave impedance we have covered. Okay, let's quickly move to the next topic. This is about the power transmission. Power transmission. Again, we are restricting our discussion to the rectangular waveguide only, right? So whenever any mode of wave propagates inside the rectangular waveguide, what amount of power gets transmitted? Okay, so but you see, we are going to apply the power transmission inside a given volume that we already have studied in the electromagnetic waves, which is given by the Poynting theorem. Have you come across the word Poynting theorem somewhere? Before applying the Poynting theorem, right, we'll apply the very simple the integration concept. So the general power transmitted is given by, it's a closed integral over a given surface, right? What is the amount of power propagating through a surface? That is dot ds. Okay, P dot ds. So I have a surface area like this, right? This is a ds, right? Assume that this is the cross-sectional area of certain waveguide. It's not rectangular, it is some other shape. Fine. So if I say that this area is the ds, and if I know that the amount of power that propagates here is P, right? I am supposed to take out a dot product, okay, and perform a closed integral of this surface. In this closed integral of the surface area, right, how much is the power propagating, you can calculate by doing the P dot ds. Okay, ds is the surface area, small surface area. Okay, so normally if you remember, the same concept has been applied even in case of the electromagnetic wave propagation and how much power gets transmitted, right? So that the same equation has been modified in the electromagnetic chapter, where we actually have a derivation, okay, to come to what I'm writing now. But right now I'm not doing that because it's not our concept, right? We already know that this power transmitted is given by half, once again the closed integral, right? It is the electric field, okay, cross product with the H fields conjugate. All right, so power is E cross H, ds remains there as it is. So there is still a dot product. It's a dot ds, right? This is the pointing theorem. So that difference is when it comes to the rectangular waveguide, right? We will try to calculate the average power, right? I'll directly write. Therefore, average power flow through a rectangular waveguide. So for calculation of the rectangular component, we'll try to calculate this way. So that is, once again, this is PTR only transmitted, but it is the average value. Okay, so I'll give an equation, then I will give an explanation why it is so. This is 1 divided by 2 times ZZ of that this thing. So integration over area A. So this is magnitude of E square dA. This is one equation. Otherwise, you can also use the ZZ divided by 2 integral over A. This is magnitude of the other component, that is H square into dA. Okay, now assume that you have voltage, okay, in a circuit. If you know the voltage, how do you calculate the power? V square by R, correct? Voltage square divided by resistance gives you the power. Okay, compare this term, very similar to this. In case of electromagnetic wave, voltage is equivalent to the E square. Okay, and resistance is similar to the ZZ. I can see the same thing in the first equation, right? E square by Z is there, you can see, right? So it's actually the same thing. We are not altering by a huge margin, right? We are simply replacing the equivalent terms to the circuit components. Whatever we measure in the circuit component, I'm trying to replace that in terms of the electric component, electric and magnetic. Similarly, if I don't know the voltage, but I know the current, means I square into R, correct? So replace I square by H square. Resistance is same, ZZ. So you can see that I square is H square. The R is there in the outside, right? I multiplied by ZZ. So H square Z I can still see there, correct? Are you comfortable with this? The notations, how we are trying to replace, right? So it's, there is a half already existing, half remains there. Either you write E square by ZZ, or you can write H square into Z, right? Anything you want you can use. Whenever I appropriately replace the terms, I still am able to calculate the required components. Okay, and I can still be able to calculate the power transmitted through the medium. Is it okay? Right. So we have a modification here. I'll write two more equations to wind up. Okay. So in case of the TM wave, what happens? Let me try to write that. Okay. So for Tm m comma n, for that kind of representation, the power transmitted can be calculated as 1 divided by, there is a 2 as it is, z I'll try to replace, that is eta times root of 1 minus lambda by lambda c the whole square. Are you okay? This is the z. Okay, into, this is actually a closed area. Area is nothing but integration happening from 0 to b, integration 0 to a, correct? That's the cross sectional area, right, of the rectangular waveguide. Then you take magnitude, the E is nothing but Ex square plus, let me correct that. Okay, all right. So you see the E component is nothing but, I can write this is Ex square, right, plus Ey square, because Ex and Ey we know, right? I'll try to write them ex square plus ey square into dx dy. You see, this becomes a double integral because one along x-axis, one dimension along y-axis. Similarly, I can actually do the same thing for hx square plus hy square, but anyway, I will not write that. It's easy to write. So very similarly, I can go for the TEMN, okay? TEM comma n wave. The power transmitted can be calculated in the following notation. So you see the ZZ value is changed now. So ZZ value gives you, there is a denominator 2 times this eta. The term goes to numerator 1 minus lambda by lambda c the whole square. Again, integration 0 to b, integration 0 to a, right? It is ex square plus ey square dx dy. That's all. Right? You know the equation for ex, you know the equation for ey. Substitute and integrate from 0 to a for x dimension, 0 to b for y dimension, multiply by the 2 eta whole divided by 1 minus root of 1 minus lambda by lambda c square to get the total amount of the power transmitted, which is in terms of the average power transmitted whenever a TM wave or TE wave propagates through the rectangular waveguide.